Have you ever wondered how a massive dam can hold back such an immense pressure exerted by millions of tons of water day after day without giving way? The answer lies far beyond the raw strength of heavy materials or solid concrete. It is a masterpiece of smart engineering, strategic physics, and continuous vigilance. When you look at a gigantic reservoir, it feels almost magical that a man-made wall can contain a force capable of reshaping entire landscapes. However, every single curve, angle, and internal component of a dam is deliberately designed to master fluid dynamics and structural stability. To understand how a dam withstands such immense forces, you first have to look at how water behaves under the influence of gravity. Hydrostatic pressure is not uniformly distributed against a barrier, instead, it increases directly in proportion to depth. The water near the surface exerts relatively mild pressure, but as you descend toward the riverbed, the weight of the entire water column stacks up, generating intense localized force at the very bottom. If a dam were built as a uniform, straight vertical wall from top to bottom, the concentrated push at the base would easily shear the structure right off its foundation or cause it to tip over. Engineers overcome this fundamental challenge by shaping the structural profile of the dam to match the natural distribution of water pressure. This is why almost all major dams are designed with a distinctly tapered shape, featuring a slender top and a massively thick base. By making the bottom section exceptionally wide and heavy, the dam gains the structural mass and footprint necessary to anchor itself against the immense horizontal push of the deeper water. This triangular or trapezoidal cross-section effectively lowers the center of gravity and directs the extreme forces down into the solid earth, preventing the entire mass from sliding or overturning under load. Beyond sheer mass, structural geometry plays a pivotal role in redirecting water pressure. Many of the most famous and impressive dams in the world employ a curved, arch-like shape that bows upstream into the reservoir. This arc is not just for visual elegance, it is a brilliant application of architectural physics. When the heavy weight of the water pushes against the convex side of the arch, the force tries to flatten the curve. As the arch tries to expand horizontally, it pushes outward against the rigid natural canyon walls on either side. Instead of the dam wall bearing the entire burden by itself, the arch shape naturally transfers the tremendous hydraulic load directly into the surrounding bedrock and natural soil foundations. The mountain walls effectively become part of the dam's load-bearing system, distributing the pressure safely across immovable natural formations. Underneath the thick layers of high-grade concrete lies an intricate internal network of structural steel reinforcement. Concrete is incredibly strong when compressed, meaning it can handle massive downward weight without crumbling, but it is naturally brittle when pulled apart by tensile forces. Water pressure creates bending forces that try to stretch the downstream side of the dam wall. To prevent catastrophic cracking from this tension, heavy steel rebar and pre-stressed steel cables are embedded throughout the concrete matrix. This combination of steel and concrete allows the structure to flex ever so slightly under changing loads without losing its structural integrity, absorbing dynamic forces such as seasonal water level shifts, thermal expansion from sunlight, and even seismic activity. Furthermore, a modern dam is far more than a static wall of steel and concrete. It is a dynamic structure built with internal comfort systems and dynamic relief mechanisms designed to handle internal stress. When concrete cures in massive quantities, it generates intense internal heat that can lead to thermal stress and micro-cracking if not managed properly. Modern construction involves specialized cooling pipes and thermal regulation systems during building, along with strategic expansion joints that allow the massive structure to adjust smoothly to changing temperatures throughout the year. Additionally, water naturally attempts to seep through small pores and natural rock fissures beneath the dam. Left unchecked, this underlying seepage creates uplift pressure, a hidden force that tries to lift the entire dam off its foundation. To combat this, engineers install deep drainage galleries and pressure relief wells inside and underneath the dam to safely collect, monitor, and drain away percolating water, neutralizing dangerous foundation uplift before it can build up. The long-term safety of a dam relies heavily on continuous monitoring and real-time structural health diagnostics. Embedded throughout the interior galleries, concrete body, and surrounding bedrock of a modern dam is a vast network of sensitive monitoring sensors. Piezometers constantly check pore water pressure within the foundation, while tilt meters and laser alignment systems detect microscopic shifts or inclinations in the main wall. Fiber optic sensors track internal temperature variations, and strain gauges measure the exact stress points across the concrete matrix. Automated seismic sensors immediately register even the faintest subterranean tremors, allowing structural engineers to assess how the dam responds to ground movement in real time. This continuous stream of data ensures that any subtle anomaly, unexpected settlement, or minor structural fatigue is identified long before it can pose a real threat. In addition to sophisticated internal instrumentation, regular human inspection and rigorous maintenance protocols are fundamental to a dam's longevity. Routine inspections involve diving teams examining submerged faces, automated drone surveys checking high spillways, and thorough engineering audits of mechanical crest gates and outlet tunnels. Over time, sediment washes downstream and builds up at the base of the reservoir, altering weight distribution and flow dynamics. Engineers manage this through controlled flushing mechanisms and continuous hydrological monitoring to keep the reservoir balanced and functioning efficiently. Ultimately, holding back millions of tons of water for decades on end is an extraordinary feat that combines physics, geology, materials science, and continuous technological oversight. A dam remains standing not simply because it is a massive block of concrete, but because every aspect of its design works in harmony with natural forces. Its tapered walls respect the laws of hydrostatic pressure, its arched geometry redirects crushing loads into solid mountain bedrock, its steel-reinforced core absorbs internal tension, and its advanced sensor networks act as a constant nervous system monitoring health around the clock. Through this thoughtful synthesis of smart engineering, protective design, and perpetual care, these megastructures safely impound immense bodies of water, continuing to generate clean energy, prevent devastating floods, and supply vital water resources to millions of people for generations.